This is where we ended last time. We finished talking about what a queue is. We defined the queue, and in fact, we defined it more Java-y by making an interface for a queue. All right, let's keep it quiet. We made an interface for a queue. And what do we want our queue to do? In queue, add something. DQ, remove something. Anyone get Dairy Queen recently? I did. It was on my mind. I know, right? There. I'm not sponsored by Dairy Queen. DQ first, which is like DQ, but it leaves the thing in the queue and is empty in size. That's the interface. We didn't need to include, typically we would want an equals. We would want our toString as well here, but we don't include those in the interface typically because, you get them for free anyways, but we override them accordingly. So this is, a queue interface. There's no implementation, it's just the signatures. Any questions about this? All right, so now it's time to implement a queue. Last time we started, when we implemented the stack, we did an array implementation, then a linked implementation. Now with the queue, we're going to start with the linked implementation, because it turns out the array implementation is kind of a pain in the ass. But we'll get there. So a linked queue. Now that we know what a queue is, let's implement it so we can actually use it. We know the what, now we need to write the how. So what are we going to need? A container, like a way to hold on to the data in the queue. We'll need a way to keep track of the front, because that's where we're going to want to remove things if we're using like a link structure. Keep track of the rear, and know the size. These things that we're going to need, we're also going to need with an array implementation, but how we do each of these things will be a little different. So we have linked queue. Spoiler, we're going to use a link structure. We need the container. We're going to use a link structure. We're going to keep track of the front with just a reference variable to a node. Keep track of the rear with a reference variable to a node. And size will just be some integer field. So this is a visualization of what we're going to do. We've got our queue. It's got a reference to the front. It's got a reference to the rear. Then it keeps track of size. Now, we could implement this without having a reference to the rear. But who can tell me what the benefit of having a reference to the rear is? Think of the context of the queue. We'll give people a second to think about it. What's the benefit here? Why would I want to do this? I don't have to, but what value do I get? Let's go with her.
You can access the rear of the queue if you wanted to. So if you want your pull from the end, you can do that if you have it.
Yes, but you're like 90% of the way there. Any other idea? I saw your hand. What were you going to say?
It just means that you're able to access the rear of the linked queue in a much faster way, so you don't have to reiterate through everything every time you find the rear.
And when would I want to know the rear?
Whenever you're adding something to the end.
Exactly. Every time I do an in queue, it's going to get added to the end. So if I didn't have a reference to the rear, and I just had a reference to the front, I would need to iterate down the link structure to find the end before I can add something there. But of course, having a reference to the rear is, really not too complex bookkeeping. There is some bookkeeping involved, and there is some complexity to it, but it's going to save us a lot of time. If I didn't have a reference to the rear, what is the computation, without even looking at the code, but thinking about what the algorithm would look like? Without having reference to a rear, and I had a link structure, a queue, with n elements in it, what would the computational complexity of that in queue be? What do you think?
N,
Why?
because you would have to iterate
Yeah. It's n because I got to go all the way to the end. Maybe I should ask this question first. What's the computational complexity, without really even looking at the code, but having an idea of what the algorithm would be to in-queue something? What's the computational complexity of in-queue with a link structure with reference to the rear?
Time constant.
It's constant. That's what you said?
Yep.
It's constant. Make a new node. Rear's next is the new node. Rear, you equal the new node. Just 3 simple operations. The amount of time it takes doesn't depend on the size of the queue. But if we didn't have that reference variable, suddenly it becomes linear. If you have a choice between a linear and a constant time operation for the same thing, you pick the constant time. So whenever you add something, it just goes to the end. You remove something, you remove from the front. So with the linked stack, all of it was adding and removing to the front of a link structure. Now it's a little different. We're removing from the front, which is really easy, and adding to the rear, which is also pretty easy when you have a reference to a rear. But there are some funny edge cases we need to consider. For example, what would be interesting about this queue if it was empty? What observation would you make? Size would be 0, but what would front and rear be referencing? No, there's nothing there. Right? Okay. What about when it's like a singleton? What about when there's only one element in this queue? What will front and rear be?
Both the same.
Yeah, they'll be aliases to the same node. And then there's the general case, which is something that looks more like this. So we do need to keep in mind those like edge cases. Oh, look at that. Spoiler. I legit didn't know that was coming up next. How about that? So that was just emphasizing those edge cases. So let's talk about the implementation. All right? Public class linked queue implements a queue. We're implementing a queue to get all that extra value like we did with the stack about telling Java that this is a queue. It can do everything a queue can do. It's good to go. So we're implementing a linked queue, or we're making a linked queue, it's implementing a queue. 2 reference variables, front and rear, size is 0. And we've got a constructor there. Constructor doesn't need any parameter. It's just to create an empty queue. And what's the case when it's an empty queue? Front and rear equal null, and size is 0. Pretty clear, right? Any questions? There's no magic here. If you think there is, you're working too hard. This is just creating an empty queue. It's ready to have things added to it, but it's just an empty queue. There's no need for another constructor, because remember, even with the other collection, with the stack, with the array stack, and the other ones, we only had 2 constructors because of, like, what if we want to initialize the array at a certain capacity, which really wasn't even necessary. But we had 2 constructors in that case. We only need the one here. So, like the stack implementation, it implements queue. The constructor creates an empty queue. Both front and rear reference null since there's no node object containing an element. Now this, of course, is going to assume we have a node class. The node class could be an internal class. It doesn't have to be, but with my implementation that you download, it's going to have it using the internal node class. So here's an in-queue. So in-queue, T, element. Great, so we get some element of type T, it's generic. We want to add it. So what are we going to do? Well, the container is these series of nodes. So we create a node with that value in it. That's what's going on line 27, it looks like right there. And then I've got to check, is empty. All right? If the queue is empty, what I do is I say front equals in queue, or to in queue, the element I'm adding. This is weird, because in queuing always happens at the rear, but this is that special case. When we're in queuing, if it's empty, front references the element we're adding. If it's not empty, rear, your next is to in queue. Right? So let's talk about that case for a moment. The general case. We go back up here. Imagine rear. I've got my new node. I say rear, your next, which is currently null, your next is getting set to the node I'm adding with the element I wanted to in queue. So rear's next becomes the node that we just created. And then immediately after that, rear equals 2 in queue. Update rear to reference the node that we just added because that is now the new rear. And increment size. Return true because it was successful. This will only ever return true with this current implementation. Is the general, okay, let's go back to the is empty. So think about what's going to happen on the empty case. Let's assume it's empty. I create a new node, 2 in queue. I'll call it TE. It's got some data in it, E for element. That's what I have. That's the first line of code in the in-queue method. Line 27, it looks like. I say, is it empty? Let's say it is. There's nothing here. I've got front, and I've got rear, and their reference variables currently referencing null. There's nothing there. Size is 0. So because it's empty, I say front, you're going to be equal to that thing. I skip the else. Rear, you equal the thing we just added. Look at that. We just caught that one edge case. Right? We caught that funny case of, well, when it's empty, and then there's one thing in it. When it's empty, there's nothing getting referenced by front and rear. When it's a singleton, when there's a single thing there, we have both the front and rear being aliases for the same one single node. So that works. But then the general case we could apply now. Let's say I'm adding a new node. Let's pretend I've got, this is my queue. E1, E2. So this is my current situation. I have a queue with one element in it, and I want to call in queue. Line 27, I make the new node with the element I'm adding. That's what E2 is. I check, is it empty? No, it's not. So I say rear, your next is the thing I want to include. So rear, your next is this. Then outside that if condition check, we update rear to not reference that, but to reference the thing that was just added. And that'll work in general. So we caught the edge case. So do you see how in-queue works differently depending on, well, is it empty or not? The actual difference in the code isn't too bad, but it's important that you understand what's going on. But remember, when in doubt, there really is only one trick to understanding what the algorithm is doing. Read the algorithm. What does the code say? There's no magic here. Draw it out if you need to. Highly recommend that. These problems are getting complex enough that you need something to help you visualize. I made a joke in lab, kids these days have all these fancy tablets that you can draw on. Back in my day, I needed a whiteboard and markers and everything. So use whatever you got. Maybe you have a piece of paper and a pencil. Great. Draw it out. All right, so we just covered that. Any questions about that? This is not trivial. I want to be very clear. It's not trivial. So if you have any thoughts, concerns, observations, points, bring them up now. I'll give you a second to think about it. Maybe if I were to rewrite this, I would change the order of that if statement. Maybe what I would write is I would say if it's not empty, set rear. And then otherwise it's the edge case. Because maybe it makes a little bit more sense if it does the general case first. This does the edge case first. If it's empty, do the special thing. Maybe I would rework the ordering there. It might make it clearer. I don't know. Just a consideration for code readability, I suppose. DQ in first. Well, let's look at DQ. It's going to be more complicated. If it's empty, no such element exception. We've got an empty queue. Otherwise, get the data from the front node. Because remember, I don't want to return the node. The node is just like inconsequential here. It's important because it's like the container. I want to return the data in that node because that's actually what I'm adding to the queue, right? So I get the data. I say front equals front.getNext. That's just removing from the front of a link structure, right? Imagine what happens here if I said front equals front.getNext. Well, that just updates this to go like this. Now, what references this node? Nothing. What happens to it then? Yeah, it just disappears. It's as good as gone. Garbage collection won't happen immediately, but it's effectively useless now. It's not there. We removed from the front of a link structure. So, return element, get the front, set size to 0, and let's skip the isEmpty check for one moment. Return element. That's the general case. Remove from the front, get the data from the front, remove the node from the front, update the size, return the data. That's the idea. But we have a funny edge case. Imagine we're in this scenario. Okay? I have a list. Pardon me, I have a queue with one element in it. And I want to remove. I want to DQ. So what does the code say? Get the data from it. Great. Front equals front.getNext. Okay, remember this one's next is like null, which is great because now front references null, which front should reference if it's an empty queue. So we set front to null, decrease size, and then we have that isEmpty check. Imagine, here actually I should eliminate this too because this doesn't exist anymore. That was used for the in queue. Will the node that E2 has, what's going to happen to that node?
It's kind of just sitting there.
It's kind of just sitting there. It's not going to get removed because rear references that node. We got a problem. When the queue is empty, both front and rear should be null. The isEmpty check is important because if I don't, rear's left kind of dangling, holding onto that node that really isn't in the queue anymore. So we're going to have a problem. So, I say rear equals null, and then nothing will reference E2, disappears. Now, I will say, I'm pretty sure, if we go look, let's look at the in queue. Let's execute the in queue pretending we forgot to update rear to be null. And let's see what's going to happen, okay? When in doubt, what does the code say? All right, create a new node, 2 in queue. It's just some node with E3 in it, great. Now, mind you, let me go down here real quick. Do I have the size? I don't. Size and isEmpty. IsEmpty just checks if size is 0. We have that size variable as well. I will say, when I DQ'd, it still updated size properly. So as of right now, it's empty. And its size is 0. Okay? But I've got this issue with rear dangling, holding onto this node that really shouldn't be in there anymore. All right, so line 27. We call in queue, line 27 runs, create a new node with the element I'm adding, with the element I'm in queuing. I check, is it empty? It is empty, because size is 0. So front doesn't reference null anymore. It goes and it references E3. Then I say rear equals 2 in Q. All right? So rear gets set there. And now what happens to the node containing E2? Garbage collection. It'll eventually disappear because nothing references it. Now the point of this exercise is to show you that despite that issue with that dangling node, an in-Q after a DQ, like the bad DQ where I didn't update that rear, wouldn't actually break this Q implementation. It would have been fine. But which implementation is better? One that sets rear to be null if it's empty, or one that leaves it dangling and in Q just kind of takes care of that situation? What's better?
Probably the one that sets it to empty.
I think so. Because it preserves a state, it ensures an important state. When it's empty, front and rear should both be null. Our implementation, if we forgot that is empty check on the DQ, would have been fine, but it's really not right. Rear should be null. So why not implement it? Oh, my voice cracked. Why not implement it in such a way that it preserves that? Also, it really then just couples this in-Q and DQ. If I didn't do that as empty check on the DQ, it really couples that DQ more to the in-Q. The DQ's correctness really depends on the in-Q. They're already coupled, but it just couples them that much more. And last, my is empty check returns is size equal to 0. I could do an is empty check by checking if front and rear are both null. Right? If front and rear are both null, that means the Q is empty. But with that bad DQ, that would kind of spoil it, right? So if you have a design decision where you're like, well, I guess it doesn't really matter, it'll still get caught, don't forget it. Also, it makes the code way clearer too, right? You are explicitly dealing with that edge case. Anyone that looks at that code goes, oh, this is an edge case check. And they're dealing with it, good. If they didn't see it, they're left going like, oh, would there be an edge case here? Is that dealt with? Is that going to work? So good, clean code has huge advantages. All right. DQ. Now first is way simpler because we don't actually have to remove anything. Just return the data from the front node. That's it. And of course, check if it's empty first. Now, what do I say? Although not true in general, with the provided implementation link queue, missing the edge case and the DQ would not actually cause a problem since the in-queue is written in such a way that it checks for empty case. Yeah? Okay. Yeah, let's go back up here. We already talked about this, but what's the computational complexity of an in-queue? It's constant time. Nothing about this in-queue has anything to do with the size of the collection, right? It's not going to take more time depending on how big the queue is. It's constant time. If we go down to DQ, what's the computational complexity of DQ? It's constant time again. I don't need to go search for anything. I just remove from the front. I've got a couple constant time operations. The whole thing is constant time. Nothing about this code depends on the size of that queue, which is nice. We like constant time things. Okay. Any questions about that queue implementation? Yes.
Is that based off the node that we wrote?
Yes. So the node that you wrote, so in lab, you would have used like a node class, a separate class. This one, if you go download the code I gave you, you'll see that it uses the node class from an internal class. Like I just have a class within the class that defines the node that's exactly the same as what you had, except it's like private static or something. So yes, this depends on the node, but there's no magic here. It's the node. There's two constructors, one where you can set the data, a set next, get next, set data, get data. Yeah. Other questions? Yes?
So in the case where you're left with no reference to that first variable, like yeah, the one that's X'd out on the board, would that be considered like a memory leak if it was running and running and running?
Can
Or
you-
is that not what memory leak is?
Well, a memory leak would cause, let me explain memory leak, and maybe that'll answer your question, because I may not have understood exactly what you were saying, but let me describe a memory leak. Memory leaks are harder to get in Java. A memory leak in Java happens when you like open a file and you never close it or something, okay? And that's just wasting RAM. Because of garbage collection, Java, the garbage collection process in the Java environment, is smart enough to go, hey, nothing references this anymore. So if the Java virtual machine starts running out of RAM for the computer, for the program that's running, it'll go and be like, well, I can actually overwrite this. This is gone. It doesn't matter. There's a lot of nuance to how it calculates it. It actually like ranks the objects based on like how old they are and whatnot. But it doesn't actually get removed from like RAM until that RAM is needed again. But for all intents and purposes, it's gone to us. And I don't need to worry, because if I kept doing this forever and put this in a loop to run forever, I'll never run out of RAM because the Java virtual machine will keep freeing it up with the garbage collector. In other programming languages that don't have a garbage collector, this causes a memory leak. Where if I didn't like delete that node, when I allocate memory with like new node, that allocates memory to a new object. And we have a topic on memory a little later in the course. But I allocate memory in the computer, in Java, in the computer. When I don't need it anymore, in some of these other programming languages without a garbage collector, I need to explicitly say delete. So new when I create, delete when I'm done with it. Otherwise, it's still going to exist in RAM, in memory. If I let that run forever, it'll eventually crash because the computer's going to run out of RAM for that program. Because although these nodes are, they're tiny, right? It'll take a while. But they take up space, and if they're never freed up, they're just going to keep existing, and eventually you've just run out of room. So that's what causes the memory leak. But in Java, that wouldn't cause a memory leak because of the garbage collection. Now, garbage collection takes, the downside of garbage collection is it takes computing resources. When Java's running your program, it's actually running a few other background processes, one of which is garbage collection. And that actually takes resources from your computer to kind of like observe your program. So that actually takes time and energy. In some of these other languages that don't have garbage collection, where you have to do all of that, there's no need for that process to be running. There's no need to waste all of those CPU cycles on checking what's going on if I need to do any garbage collection. So, pros and cons. Realistically, use garbage collected languages. But, yeah. Great question. Hopefully that was fun for others. Other questions about this implementation of a queue? Now this is just one idea of a queue. We can implement another type of a queue. We can make a linked queue called a linked priority queue. A priority queue, the only reason I'm bringing this up is it's going to be used for assignment 3. There's a bajillion different variations of a queue we can talk about, but I'm going to talk about a priority queue. This is probably best explained with an example. Imagine getting triaged at the hospital. It's first come, first serve, right? unless someone and if you're there for stitches, it's first come, first serve, unless someone comes in with a gunshot to the arm or something, right? They're going to jump the line. So there is this first come, first serve, but you're ranked based on a priority, on how quickly you need treatment. So that's the idea of a priority queue. You in-queue the elements, and when you in-queue them, they have a priority associated with them. Those that have a more important priority, whether it's a lower number or a higher number, really depends on the needs. But those with the a more important priority, they get in-queued first. The thing that was added with the most important priority gets removed first. The thing that's in-queued that has the lowest priority would be the last thing that would ever get dequeued. And if you have a tie on priorities, that could be a first come, first serve thing, whatever. So it's a queue, but it's not based on in-queue time. It's based on priority, is how they're dequeued. So everything, now, okay, we have a design decision to make. Imagine having to implement this priority queue, which you will. How do I want to do this? Should we, when in queuing, search the link structure, assume the link structure is ordered, with the thing with the most important priority at the front, and the thing with the least important priority at the rear. When I in-queue, what I could do is search through that link structure until I find where this new node I want to add with its priority goes, and then insert it there. Then, dequeue is just remove from the front, just like before. Really nothing special, you just dequeue. Now, that dequeue would be a constant time thing. It's just, get the element, remove it. But the in queue is different. Because before, with a regular old priority queue, in queue, you just go to the rear and you add it there. It's constant time. But if our collection is sorted, I got to go through, and if I have a queue of n elements, how many things might I have to look at to find where that element goes, that one I want to in queue? N, all of them. So suddenly, this in queue becomes linear. Okay, how about alternatively, we leave in queue alone. In queue, you always add to the end. No matter what the priority is, add to the end. But then on a D queue, you have to do a linear search for the element with the lowest priority. Then you remove that element from wherever it is in that link structure. Now, we saw the code for adding, removing to the front and middle and whatnot.
Would it be highest or lowest priority?
It depends on what you want it to be. Yeah. I think for our, my back's killing me from snow shoveling yesterday. Oh. I think for your assignment it's going to be minimum based, right? But it's arbitrary. So with that implementation, the in queue is constant time, but the D queue becomes linear. Because I have to do a linear search for the element with the lowest value. If it's a minimum priority queue. Which of these two ideas would you choose and why? Take a moment, think about it. You can talk amongst yourselves. What would you use? Or does anyone have, what do we think? I want to hear what some people think. Let's try to get different people now. I don't want always the same people. Come on, we gotta get something. I heard you talking, I know you have an idea. Yeah, what do you think?
Like, I'm a little unsure, but like, wouldn't it like just really depend on the situation? Like, if you're always like, if you're seeing more or eating something more than you were DQing, you would not want to. You wouldn't want to delay your search at the beginning there. You want it at the end because you're DQing less. But if you're DQing
Yeah,
more,
you make a lot of sense. The answer really depends. There's, first and foremost, there's no obvious answer. There's no silver bullet. One's good in one case, one's better in another case. Now we can play a game where maybe we can do a little digging. You can never DQ more than you NQ. That's impossible, right? You can't remove things that don't exist. So presumably, it could be possible that you do more NQs. And that's always constant time, great. But those DQs are linear. Not bad. The alternative is to flip. But where the NQ is linear, I actually have a bit of a trick here. Anyone have an idea on what the trick? There's a little bit of a. What's the word I'm looking for? There's a little bit of a. It's linear, but there's a little bit of a trick we can do to kind of eliminate some work. When DQing, the elements are in an arbitrary order. So when I need to look for the lowest thing, I need to look at all of the things. I have to look at all n. Right? Because until I've looked at them all, I won't know which one has like the lowest priority, assuming I'm minimizing priority. But with the linear NQ, they're sorted. They have to be sorted. So when I go, I don't always have to look at all n. Right? If I'm going and I've got some value like 17, and I see priority 1, 4, 15, 22, I don't need to keep going, do I? I know 17 comes between 15 and 22. So, I don't know. Now, it's still linear, don't get me wrong. But, that's a consideration. In practice, you would use neither. Both of these are terrible. There's a much better idea that we'll kind of probably talk about later in the course. But these are the two implementations we're going to worry about, and one of these, you're going to implement it in assignment 3. Who here's done assignment 2? One person. Nice. Nice. All right. Great. And here's just some arbitrary code to just play around with the linked queue. Again, note that the reference variable is a reference variable for a queue, not a linked queue. The instance of the queue we're making is a linked queue. But the reference variable, all the reference variable cares is that it's referencing something that is a queue. And because a linked queue implements the queue interface, it is a queue. Cool? Great. So there's a linked implementation of a queue. Any questions, any last questions about the linked implementation before we jump into the array implementation? Now I'm going to warn you, this one gets a little bit more complicated. Now a little bit more complex. Use that word instead. It's really not too bad, don't worry. But there is a bit of a jump in complexity here. And I think the way to motivate this jump in complexity and why it's necessary is to work through some ideas. So we want to make a queue, but with an array. So the container is going to be an array. We need a way to keep track of the front, we need a way to keep track of the tail, and a way to keep track of the size. A linked structure was used as a container for a queue. Now we're going to use the array to implement the queue. So here's idea 1. How about this? We will have it so the front is always index 0. So that way when I need to dequeue, it's always at index 0. The rear is the next available spot. So when I in-queue, I just in-queue to rear. And the size happens to also be rear. Right? Great. So here's the queue. If I in-queue, I just add it to rear and increment rear. If I dequeue, I remove the thing at index 0. I have to shuffle everything down though. And I decrease rear. Now the first question I have here, will this implementation work? I mean, we only talked about it very superficially. So there's no like funny little bugs that we might need to think about. Just, would that idea work? Could you implement an array queue with this idea? Say yes.
Yes.
Of course you can. There's nothing wrong with it. What's the computational complexity of an in-queue? I guess we've got an expand capacity situation, right? Because if I'm in-queuing and I run out of room in my array, I might need to, expand capacity, which we know is linear, but we kind of talked about that amortized thing, where kind of it's constant time. So in-queue is constant time, which is great. We like constant time. Even though it's amortized, we're still happy. But the problem is the dequeue, right? When I remove the thing at index 0, and I have n elements in my queue, when I dequeue the thing at index 0, I now have a hole at index 0. There's nothing there. So I need to move everyone down 1. Everyone's got to shuffle down towards 0. If there's n elements in that array, how many things need to move? N. What's the computational complexity of this? N. It's linear. If n is twice as big, it takes twice as long. This isn't bad, but what was the computational complexity of an in-queue with the link structure? 1. Constant. Dequeue, constant. This, we have constant, but a linear in-queue, or pardon me, a linear dequeue. Maybe we can do better. Maybe we can come up with a more clever idea. So here's idea number 2. What if, okay, so keeping front at 0, ensuring 0 was always the element at the beginning of the queue was the root of the problem. Because we had to shuffle everything down 1. So what if instead we keep track of the front, we keep track of the rear, and when we dequeue from index 0, we just update front. Forget it. Index 0, whatever. It's not used anymore. That's idea number 2. So now when you in-queue, it looks like that. When you dequeue, it looks like this. If you want to know the size, we just take the difference between the front and the rear. Ooh, rear is actually wrong. There's a mistake in that figure. Uh-oh. That should say rear should be 5, not 4 in that example. Like it is here. Look at that. Ooh. Great. Would this implementation work?
Yes.
Yeah. What is the computational complexity of an in-queue?
1.
Constant time. Amortized, expand capacity, whatever. What's the computational complexity of a dequeue?
Constant.
Constant time. Just remove from the front, update 0. Update the index for the front. Constant time. But can anyone see maybe the right word to use here isn't problem, but can anyone make an observation about what's going on here? A thought, a concern maybe?
How much space is that gonna take up at the end of all this?
Yeah, like index 0 is now useless. Index 0, this is like a memory leak. Index 0, we can never get that back. Right? Because when I in-queue, I'm always adding to the end. Expand capacity, expand capacity, expand capacity. Let me put it this way. Assuming a similar number of in-queues and DQs as idea 1 versus idea 2, how frequent, relatively speaking, between idea 1 and idea 2? Idea 1, we shuffled everything down every DQ. Idea 2, we didn't. But we got a way faster DQ. Constant time. How often will expand capacity need to be called between the two implementations, between idea 1 and idea 2?
A lot more for idea 2.
Idea 2 is going to require a lot more because we've got that wasted space, right? Idea 1, if I did a DQ, I shuffle everything down, I get one more in queue now before I have to do an expand capacity. Idea 2, it doesn't matter. I could do n in queues, n DQs, and that n plus 1th in queue still needs to call expand capacity. Where idea 1, it wouldn't. Idea 1, well, it would just add to index 0. So this calls expand capacity a lot more often, and we're wasting a lot of space out front in that array. It's lost, forever lost. And I will end here before we get to the good implementation.